is just really the basics of XRF, of what the heck is going on. So you have an excitation source, okay? And it's either like we're using a tube or radioactive isotopes. And what that source does is that it causes the atoms in the sample to, become unstable. And how it does that is it knocks off electrons, inner shell electrons, and causes instability with the atom. And then the atom, by moving the electrons around, outer shell electrons move into the inner shell, it wants to stabilize itself. And then when that happens, it gives off energy. That energy has come back to the detector, and it's captured, and then goes through the processor and everything, and displays an answer, either quantitative or qualitative, in this case, all quantitative. So this just shows a little bit about what's going on. So you've got the tube, and it knocks out either a K or L shell electron, the two most inner shells, okay? But why one or the other? Well, it's all depending on the binding energy of that electron shell to the nucleus, okay? For instance, remember I mentioned it's a 40 keV tube. Right at the window, it's less than that, okay? So let's take lead. That's easy. And a lot of you are going to deal with lead. We use the L shell of lead. And the reason is it takes about 23 keV of energy to dislodge an L shell electron from lead, okay? But it takes about 88 keV of energy to dislodge a K shell. Well, we don't have 88 keV, so we can't dislodge. We don't have enough power to dislodge the K shell, but we do the L shell, okay? Other elements, we can do the K shell, copper, nickel, molybdenum, things like that. We have enough power to dislodge the K shell, all right? So that's what we would use. And we do the other ones as well, but the thing is, the energies coming back are so weak they don't get to the detector, just not measurable, or they're down in visible light or something like, or UV light, I should say. So we're using either the K or L depending on the element. So when we knock one off, the other electrons get excited, go, oh, there's an opening in a better shell. You want to get as close to the nucleus as you can. If we thought like electrons, that's what we'd want to do. We'd keep moving closer to the nucleus. So when that happens, say an L shell drops into the K shell, because the binding energy is better, it takes less energy to be a K shell electron than it does to be an L shell electron. So it gives it off in the form of an X-ray. And every element in the periodic table has its own signature X-ray energies. Okay? So they come back, bounce off our detector. We go, oh, that's 10.5 keV. That's lead. Or it's 12.6 keV. That's lead as well. Okay? So anyway, you'll see when we get into the spectrum. So that's what's going on. We're knocking, the atoms are just trying to stabilize. And then we're counting the X-rays that are coming back. And then you see these peaks are growing based on the number of counts, the count rate in those energy lines. And the instrument knows what element is what energy because we've told it. All right? We define an energy region for each of the elements that are calibrated into the system. And then, there's mathematical algorithms in there that are way over me that figure all this out. So we define a region, as I said, so we tell the instrument, okay, gold is this region, lead is this region, whatever, okay? And then with the mathematical algorithms, they're doing background corrections to separate noise and signal and so forth. So quantitation is in 3 steps. You don't really have to remember all these things. But this is what, I just wanted to go through this very quickly so you get an idea of what's happening, okay, and why we need X-rays to do this job.